Okay, today we're going to be looking at binomial expansions of things of the form 1 plus x to the power n for values of n that are not positive integers. So, we know previously we've looked at binomial expansions when we had something like this, 1 plus x to the power n. We would do n 0 plus n 1 x plus n 2 x squared plus n 3 x cubed plus all the way up to n x to the n. And if you did work that out, you got 1 plus n x plus n minus 1 over 2 factorial x squared plus n minus 1 n minus 2 over 3 factorial x cubed plus all the way up to x to the n. And this was true when n was a positive integer. Now this also, we can also have this can also be used as the general binomial theorem. When we have this expansion, but we're going to take this last term away, because as we will see, this will not, it won't get to that part, because we're going to have n is rational, but it can be negative, and the modulus of x is less than 1. Now, this holds, so when so there are two very important differences when n is not positive. And firstly, the series is infinite. So that's why we took that last term. If you think about as this grows, if n's negative, these are, you're never going to get it tending towards n. These are just going to keep going and keep going and keep going. And the other important difference is the expansion is only valid for the modulus of x less than 1. Now, there's a proof for this, but that is something you would have to do at university level. So for now, let's just consider two examples. So we're going to consider firstly when n equals minus 3. So when n is minus 3, we've got 1 plus x to the minus 3. So that's going to give us, let's write it all out. 1 plus nx plus n minus 1 over 2 factorial x squared plus n minus 1 n minus 2 over 3 factorial x cubed. Then we're going to have n minus 1 n minus 2 n minus 3 over 4 factorial x to the power 4 plus, and so on and so forth. So when let's put our value of n in now. So we will have just 1, then we'll have minus 3x, then we'll have minus 3, minus 3 minus 1 is minus 4, over 2 factorial x squared, plus minus 3 again, then we'll have minus 4, then we'll have minus 5, looking at these, 3 factorial x cubed, then we'll have again our minus 3, minus 4, minus 5, and this time minus 3 is minus 6, and then 4 factorial x to the 4, and so on. So when we've got when n's minus 3, this, we're always going to have another term. We're going to keep going and keep going. The sequence is going to be infinite. And if you work all that out, you'll get 1 minus 3x plus 6x squared minus 10x cubed plus 15x to the power 4, and so on and so forth. So that's our first one we want to do. Now, what if we have n equal a half? So we'd have 1 plus x to the half. So we'd be plugging in our half into these terms. So with this we'd have 1 plus a half x plus a half, then a half minus 1 is going to be minus a half, over 2 factorial x squared plus a half minus a half, then minus 3 over 2 over 3 factorial x cubed, then plus half minus a half minus 3 over 2, then a half minus 3 is going to be minus 5 over 2 all over x 4 factorial, sorry, x to the power 4, and so on. So again, we've got this infinite series, and if we work out all those values, you'll have 1 plus a half x, not half, not plus, sorry, minus an 8th x squared plus 16x cubed minus 5 over 128x to the power 4 plus so on and so forth. So we can see that the sequence of coefficients forms an infinite series. You can keep adding more and more coefficients in. Now when the modulus of x is less than 1, the binomial series converges. And has a sum to infinity. In the same way as when we do geometric series, it converges when the modulus of r is less than 1, where r is the common ratio. So that's the same idea. Now, just as a wee bit of maths trivia, Isaac Newton is accredited for the generalised binomial theorem for all rational powers. A poet once wrote, poetry and maths go together. A poet once wrote that Newton's binomial is more beautiful than the Venus de Milo. The truth is that few people notice it. So I'll let you ponder that to think whether it is true or not. But we are going to go on and do some examples. So expand 1 minus 3x to the minus 2 in ascending order ascending powers, sorry, of x up to and including x cubed, and state the range of x for which values x is a valid expansion, sorry. So we've got n equals minus 2, and let's let so when we've got our, so we've been doing 1 plus x to the n, and n's minus 2, but we can replace the x by just putting in minus 2. It's just x, so this is minus 3, sorry, to the minus 2 here. So we have our expression 1 plus nx plus n to the n minus 1 over 2 factorial x squared plus n minus 1 n minus 2 over 3 factorial x cubed, and that's where we want to go. So here we've got our 1 and we've got our minus 2 for here, and then our x is going to be minus 3x. And then we've got plus, now it's minus 2, and then it's going to be minus 3 over 2 factorial, and then we have minus 3x squared plus minus 2 minus 3 minus 4 over 3 factorial, and then it's minus 3x cubed. Now when you're doing these, use your brackets, because it's going to be really, I'm going to actually put this in brackets too and just put a plus sign here because it's really, really easy to make mistakes with signs. So here we'll get 1, and this is then going to be plus, because the minus 2 times minus 3 is going to be plus 6x. Then we've got, then we're going to have another plus, because this is going to be, it's going to be 9, and these minuses will cancel, so it's going to be 27x squared. Then we're going to have more minuses cancelling, so plus 108x cubed, plus so on and so forth. And for the expansion is valid for the modulus of minus 3x to be less than 1. So for x, modulus of x to be less than a third. Let's look at another example. Find the first 4 terms of this 1 plus 2x squared to the minus 4, and state the range of values of x for which the expansion is valid. So we've got n equals minus 4, and instead of having our x, we're going to replace x with 2x squared. So we'll have 1 plus 2x squared to the minus 4, and this would give us, I'm not going to write out the whole expansion thing again, so we'd have 1 plus, then we've got the n would be minus 4, and then our x is 2x squared, plus, our n's again minus 4, n minus 1 is going to be minus 5, over our 2 factorial, and then this expression is our x squared one, so we'd have 2x all squared. Oh, that's squared already. Plus minus 4, minus 5, minus 6 over 3 factorial. Then we've got 2x squared, and that's going to be cubed. Now, we wanted how many values? 4 terms. So 1, 2, 3, 4 terms. So now we have to just work everything out here. So this is going to give us, oh, that's a minus, because we've got a minus here, so it's minus 8, 4 times 2 is 8, x squared, plus, chucking this away in our calculator, we will get plus 40x to the power 4. Now remember, this 2 here will have to be squared. Plus, and again this 2 is going to be cubed and then multiplied by whatever this is going to come out as when you chuck it into your calculator, and it's going to be a minus, not a plus, 160x, and then x squared cubed is 2 times 3 is 6. It's not very nice, 6 plus, so on and so forth. Now, we want the range, so we look at this, and we want this to be, if this is equal to 0, we would then be, remember we're looking at the modulus, 2x squared is going to be less than 1. And then, so it's a modulus, sorry. And then we would do x squared would, the modulus x squared would be less than half, but this is x, so it's going to be the modulus of x is going to be less than 1 over root 2. Let us do another one. It's going to be a wee bit more trickier. So find the coefficient of x cubed in the expansion of x minus 5 over 1 plus 2x. So, you're thinking expansion, you're going to think binomials. If you see a question like this, think, well, how can we expand it? So we think binomials here. So we're going to rewrite this as this. And then we're going to deal with this part first. We're going to expand this part. So n is going to be minus 1, and we're going to replace x by 2x. So we're going to expand 1 plus 2x to the minus 1. And that's going to be just 1 plus our n, which is minus 1, and our x is 2x, plus minus 1 minus 2 over 2 factorial, then 2x squared, and then plus minus 1 minus 2 minus 3 over 3 factorial 2x cubed. Remember, it's cubed everything in here. Now we're wanting the coefficient of x cubed, so we're going to go up to get our x cubed coefficient, but we need to be careful because this expansion is going to be multiplied by this. So we're going up to here, but the answer to this part is not going to be the answer to the question. So let's do all the calculations here. So we get 1 minus 2x plus 4x squared minus 8x cubed, so on and so forth. Now we take what we had originally, so we had our x minus 5, and then we're multiplying it by our expansion, so we have our 1 minus 2x plus 4x squared minus 8x cubed, plus and so on. Now we have to multiply out the bracket. And because we have an x here, that's going to mean when we multiply this, we're going to get another x cubed. And when we multiply this by this, we'll have an x cubed here. Now, we only really need to think about the terms with x cubed. Now we can redo this with x 1 minus 2x plus 4x squared minus 8x cubed minus 5 1 minus 2x plus 4x squared minus 8x cubed. Now let's look where we're going to get x cubed. That's what we're thinking about. So if we multiply 2, that's not going to give us an x cubed. That's not going to give us an x cubed, but this is. So we're going to get 4x cubed. And here, that's not going to give us x cubed. That isn't, but this is. So we've got minus 5 times 8, which is going to be 40x cubed. So that will give us 44x cubed as our coefficient for the x cubed part. So I hope that helps.